All right, so in this video, we're going to start out talking about the work energy theorem. And to start out with that, we need to review a couple of things that we already talked about last semester. These first four blanks are actually review because they say review. So I want you to take a minute, pause the video, and see if you can figure out what goes in those four blanks. Okay, so last semester, let me get this closer right here. Last semester, we talked about work and energy. These words should at least sound familiar to you. I understand if you don't necessarily remember them very well. But I gave you two definitions for work, and I told you there was going to be a third one coming up. And that third one will be right here. But let's first review the first two and review the definition for energy. So we said work is done when a force, number one, moves an object against another force through a distance, and usually that force is called friction. Second definition for work is when a force causes an object to accelerate. When a force causes an object to accelerate. So those were the two big definitions of work. Remember the three ways to accelerate: speed up, slow down, change direction. So anytime that any of those things are happening, work is being done to cause it. And then we said energy is the ability to do work. Energy is the ability to do work. You can't do work, you can't move an object against a force, and you can't cause an object to accelerate without energy. Energy causes that work to be done. Okay? But now we want to think about a slightly different scenario to explain the work energy theorem. So let's say you have a bowling ball on the ground. All right, and we want to lift it. It's 10 kilograms is its mass. We want to lift it up to a height of 2 meters. And we want to know how much work we have done to do that. So we remember talking about work before. We know the equation for work, at least the one that we used before, is work equals force times distance. Now, the equation, or the force rather, that we use to lift that bowling ball, remember that there's a special thing happening anytime there's lifting going on. In order to lift an object, the force required to lift is equal to the weight of that object. And if you remember, weight is the force of gravity. We say Fg, and the equation for weight is Fg equals mg. Mass times lowercase g is the acceleration due to gravity, which was 9.8. Remember that? And we're going to use positive 9.8 here because we're talking about energies. Therefore, that's what these three little dots means. Therefore, our equation becomes work equals not force times distance, but the force is the weight. So we're going to first of all throw the weight in there. We're going to say mg times distance. That mg is the weight. The weight is the force required to do the work. So now we can plug in numbers and say the mass is 10, g is 9.8, and the distance that we lifted the ball was 2 meters. 10 times 9.8 times 2 happens to be 196 joules of work. You did 196 joules of work to lift that ball to that height. And then the next question is, how much potential energy does the ball now have at that height? So we also learned the formula for potential energy last semester. Potential energy is mgh. So now we go, okay, mass, g is positive 9.8, height, the height that we lifted the ball was 2 meters. So we go 10 times 9.8 times 2. And if you do that, you will get 196 joules. And you'll notice that those two are exactly the same. That's not a coincidence. I'm doing this on purpose. And so it doesn't really matter what height we lifted the ball to. You could lift it to a height of 4 meters, 1 meter, 1.5 meters. No matter what height you lifted it to, these two numbers will always be exactly the same. Therefore, there's a really important conclusion that we have to draw from the answers to these two questions. And the question is, where did this energy come from? The ball now has potential energy. Where did it come from? Because I want you to begin to understand that energy is a substance that flows through systems, kind of like money. We're going to talk about energy and compare it to money today. You can chart the flow of money. We're going to talk about and how to trace energy flow through a system. You might have seen that website before where you can trace an actual dollar bill and know exactly where it's gone based on the number on it, the serial number. I want you to be able to trace the flow of energy. So the question is, where did this energy come from? Well, it's no secret that the work done matches the energy. Therefore, the energy came from the work done on the ball. So let's write that potential energy came from work done on the ball. Really important point to understand there, that potential energy came from work. And that's always the case with potential energy. Even when you're walking up the stairs, you're doing work at that point to go up the stairs, and the work you do gives your own body potential energy. Work always produces potential energy, and potential energy always comes from work. And therefore, this leads us to the third and most insightful and important definition of work. Work is therefore change in energy. This is so incredibly important. As a matter of fact, this is like the center of the entire course right here. Work is a change in energy. That means anytime energy is changing amounts, up or down, or anytime energy is changing types, transforming from one type to another, work is being done. Because remember, the law of conservation of energy, which we're going to talk about later, but most people know anyway, the law of conservation of energy says that energy can neither be created nor destroyed. Just like money can't really be created or destroyed. It's always there, it's always somewhere, but it can change hands. In the case of energy, energy can't be created or destroyed either, but it can change forms. So work is being done when energy is changing amounts or when it's changing types. A lot of times we're talking about energy transformations. For instance, the light that's coming out of your screen right now, the LED on your screen, if it's a phone or if it's a computer screen, is producing light energy, and there's electrical energy coming into that device, and there's work being done to convert electrical energy to light energy. That's work. So that brings us to equation number 17. That's the work energy theorem. And we remember that work equals force times distance. That's still true, but we're going to throw something else in the middle. And this one, these two are going to be on the ends. Remember, work is a change in energy. And the symbol we use for change is delta. Delta E, change in energy. Now, we need to define this because anytime we calculate a change in anything, it's always final minus initial. So the change in energy is EF minus EI. Final energy minus initial energy. And this is really the part that we're going to use today. We're going to say change in energy, but this is really what we're going to use. We're not ever going to actually write down delta E because delta E is not useful. This is because that's the way we calculate it. When we use EF minus EI, you need to know that for us in this class, at least right now, there are basically three choices that you have for EF and EI in, as far as types of energy. And you have to make this decision every time you have these. Final energy and initial energy can be either potential energy, or it could be kinetic energy, or we could have zero energy. Potential, kinetic, or zero energy. All right, so before we move on, I want to talk about energy flow. Okay, I want to look at energy flow in this specific scenario because it's very important not only that you understand how to calculate this stuff, but you understand where energy is going. This is so important in today's world because everything is about energy. So at the top, we know that this ball has some potential energy. Question is, where did that potential energy come from? Well, it came from work done on the ball in the middle. The work is what gives the ball potential energy, but the work actually, what it's doing is it's transforming something else to potential energy. So the question is, what was the energy before it was potential energy? Well, the ball is moving here in the middle, and it Therefore, we have kinetic energy here. So kinetic energy is being transformed to potential energy. But what was the energy before it was kinetic energy? Well, the ball is moving because your muscles are moving it. And your muscles get their energy from a chemical. So we're going to say this is chemical energy. Chem-E stands for chemical energy. Chemical energy in the form of a chemical, a molecule called ATP, you might remember from biology. So this is energy flow through this very simple system. The energy started in your muscles in the form of ATP. Your muscles contracted and produces kinetic energy. The kinetic energy lifts the ball upward. That kinetic energy on the way up gets converted to potential energy because now the ball has height. So remember, potential energy related to height, kinetic energy related to speed or movement. That's a really very simple example of energy transformation through this very simple system. Now, I want you to consider this. This is going to be really, really useful for you to compare this to a bank. Okay, so here's the bank. It's where you put your money when you go to work. The bank is thinking about money in the bank is really an easy way to understand the work energy theorem. So imagine that energy is the amount of money you have in the bank right now, right? In other words, it's your balance. It's the balance on your account in the bank. How much money you actually have in the bank, all right? And let's just say that's $50. I don't know. $50 in the bank. That is equivalent to energy. There's basically two things that you can do with the money in your bank, all right? You can either put money in, or you can take money out. Very simple. These are called deposits, and this is called a withdrawal, or spending your money, right? Deposit and withdraw. These two things can be thought of as work. And you might remember when we talked about work and energy, we said that the unit for energy was joules, and the unit for work is also joules. Well, that's obvious to see why that is now. It's the same reason why the unit for deposits and withdrawals in this country are dollars, and the unit for the money you have in the bank is the same, dollars, because it's all the same concept. It's a substance that's flowing in and out of a certain place, flowing in and out of this system. So work done simply changes the amount of energy we have in here. Depositing money is like positive work. We're putting energy into the system. Withdraw is like negative work. You're taking money out of the system. So in this particular system with the bowling ball, what we were doing on the bowling ball was positive work on this side because your muscles were putting energy into the system. You had zero energy down here on the bottom. The ball wasn't moving. It had no height. There was no energy. And now we had potential energy up here at the top. We actually had 196 joules of potential energy. Where did that energy come from? Well, it came from the ATP in your muscles, but your muscles did work to put some money into the bank, into the ball. You put 196 joules of energy into the ball. In other words, in terms of money, you deposited 196 joules into an empty bank account, $196 rather. And how much money do you have at the end? It's very simple. You have $196 in the bank. The amount you have in the bank is the amount of energy. The amount you put into the bank, or the deposit right here, is the work. That's the simple comparison, and I'll continue to refer to that sort of concept as we go along. All right, so in the next video, we're going to learn how to apply that concept and solve these problems.